Good afternoon, ladies and gentlemen. In this video, I'm going to do the preparation problems for practice A of chapter 20. So this is electromagnetic induction. So what I have here I'm showing you is the PhET page, and I'll give you the link to this, for Faraday's law. So we're going to be using Faraday's law equation, it's always about an equation, to solve the problems for the homework problems. But I want you to understand where it comes from. So right here we have a magnet, and you can change where you have which one's north and which one's south. And so I'm going to show you the magnetic lines and magnetic field lines. Right here I'm going to click on where it says field lines. There we go. So with the magnet, you're going to notice that from the outside, the field lines go from the north to the south, from the north to the south. See how they get further apart because it's less strong, not weaker magnetic field the further away you are from the magnet. And so these lines are closer together, and the strongest is going to be at the north, at the end of the North Pole or at the end of the South Pole. But in the inside the magnet, the field lines are going from the south to the north. Okay, so you have to visualize it's going from the south to the north on the inside. Now let me flip it. Okay, and so now it's the same thing. On the outside, it's going from the north to the south. On the inside, from the south to the north. So we have a magnet here. Now let me turn off those field lines. We have a magnet, and you'll notice here I've got 4 coils, and one end of the coil is connected to one side of the light bulb, and the other side of the light bulb is connected to the other end of the coil. And that's it. I don't have any batteries or anything to make current go through, which is how you would expect you would need to make the light bulb turn on. But if I take a magnet and I push the magnet inside the coil, the light bulb turns on, and it turns off, then it turns on again. And it turns out that if there's a change in the magnetic field through the coils, you're inducing an electrical current, which is why the light bulb turns on. All right, so this is just 4 coils, or I should say it is 4 coils. And up here, I'm gonna have 2 coils. So I wanna know if you can tell the difference if you have 2 coils versus the 4 coils. Oh, it looks like a lot brighter. The 2 coils turns on, but 4 is a lot brighter. Well, what if I connect a voltmeter? Let me put in a voltmeter. There we go. So I have a voltmeter, and it's connected to both sides, or each side of the light bulb. And you're going to look at the cursor, I'm saying here, the indicator, and see how far it goes. We'll start with the 2, and it goes about halfway, let's say 45 degrees. There you go. That's as far as it goes. But if I double the amount of coils, notice that there's 2 coils here and here's 4 coils here, what happens to the voltage that's induced? Oh, it's a lot brighter. Notice that the needle went all the way down to the end. The needle, that was the word I was looking for, needle. Okay, so this is because of Faraday's law. So let me switch over to the table here so you can see the equation. All right, so I draw your attention to a handout that I provided. What is Faraday's law? Faraday's law says any change in the magnetic environment of a coil of wire will cause a voltage, or an EMF, to be induced in the coil. So if you have the voltage induced in the coil, you're going to get a current induced as well. No matter how the change is produced, the voltage will be generated. The change could be from changing the magnetic field strength, or moving a magnet toward or away from the coil. So you notice that when I was pushing it in, or I was pulling it out. Moving the coil in or out. So I could take the coil and move it around the magnetic field, around the magnet. Rotating the coil. All these ways are how you can generate a voltage. And here's your equation. So please take a look at this worksheet. So it depends on the number of turns. B, if you'll remember from last chapter, is your magnetic field in Tesla. And here's the area. So how big is that coil? What is the area? Sometimes you just see just B and then delta A. Maybe it's A and delta B. So it's got to be a change. As long as there's a change in one of these things, and you'll get some voltage generated, or EMF, in a certain amount of time. Okay, so the number of coils, change in magnetic field, the area divided by the time. And that is Faraday's law. So take a look at the rest of the worksheet or handout. to get some better idea of what Faraday's law is. All right, so let's take a look at the problem. And this is on page 739. There you go. We'll start with number 10. It says a flexible loop of conducting wire has a radius of 0.12 meters. So I immediately drew something like this. There's my loop. It's kind of a loop. I have it laying down. And let's say my magnetic field is pointing down in this direction. Okay, so I have 90 degrees. Always got to be 90 degrees to have the maximum amount of change. Okay, so I have a flexible loop conducting wire radius of 0.12. So the radius of this loop, remember I have it kind of laying down sideways, this radius, the radius right here is 0.12 meters. Okay, 0.12 meters. It's perpendicular to uniform magnetic field with the strength of 0.15 Tesla. Okay, so I know that B is 0.15 Tesla, as in the figure. Here's the figure. So if you remember, X means that you're seeing the back part of the tail. So dot means it's coming out of the paper. So it's going down from, say, my pen through the paper down the table. That's the direction of the magnetic field. And here's my loop. Probably has a little handle that I can touch the handle as I move it across the magnetic field to induce a voltage. Okay, it says the loop is grasped at opposite ends. So you're going to take your fingers here, and you're going to pull it apart, and it's stretched. It's grasped at opposite ends and stretched until it closes to an area of this right here. All right, so I've gotten a point. I'm going to call that area 2. So here's an area 1, and what's the first area? Well, I remember that area is pi r squared. So area 1 would be whatever pi times 0.12 squared is. And area 2, now that we squished it, is much smaller. I'm going to say here it's 0.003. Is that right? Yeah, 3 times 10 to the negative 3 square meters. Okay, as in figure B below. If it takes 0.20 seconds, okay, there's my delta T, 0.20 seconds. All right, seconds, because my S's look like 5s. Find the magnitude of the average induced EMF. What is the EMF induced in the loop during this time? That's what we want to know. Let me grab another piece of paper here underneath. Okay. Hopefully you can still see everything there. I'm going to cover a little picture since we know what we're talking about here. So we're going to get the formula from our worksheet or handout. So the induced, and it said voltage generated. Okay, that's fine. I'm going to say EMF induced, because remember EMF is also the voltage, is equal to negative N, and it says change in B and change of A. I'm going to just write it both ways. Just change B and change A. Okay, so in this case here, the area changes. So I really just need one of the changes. This one's not going to change. So it's just B times the change of area, all divided by delta T. Okay, so what do we have here? Well, we've got only one. There's only one loop. One loop around. I didn't tell you that there was more than one. It just said flexo loop. So we know that N is equal to 1. N is equal to 1. All right, so we have 1, and then B is 0.15 Tesla, 0.15 Tesla, and change of area. I need to do the change of area, so maybe I should have done that first, but that's okay. Area 2 is 0.003. Maybe I will here. Let's do the area 2. Area 2 we got is 0.003. Area 1 is pi r squared, which is pi times 0.12 meters squared. Let me see what that is quickly. Here we go. 0.12 squared times pi. Here it is. So this guy here is 0.0452389. I'm just going to leave that in my calculator. All right, so I want the change of A. Change of A. Remember, delta is the after minus the before. So the after is 0.003. 0.003 minus this stuff right here I got in my calculator, 0.045238.9, etc. I'll just leave that in my calculator. All that divided by the time. And the time is 0.2 seconds. 0.2 seconds. All right, so I'm going to go ahead and have that and subtract that from 0.03. A couple ways I could do that. One is I multiply it by -1. That gives me the negative, and I add it to 0.03. Or I can just subtract it from 0.03 and switch the polarity. I'm going to multiply it by -1. There we go. Now I can say add that to 0.003. There we go. Okay, now I'm going to take that. That's this part here. I'm going to multiply it by 0.15 times 0.15, and then I'm going to divide it by 0.2. Divide it by 0.2. And I get a negative 0.031679 volts. Okay, so let's put that into, look at our, how many we have, one probably here. Let's just give you one, significant figure, 2 there, so 1. So we could say 0.03, or I would take it, I always take it an extra. So I'm going to give it 2. You could say here 0.032, or we could say negative 0.032 volts. Or we can say 3.2 times 10 to the negative 2 volts. So there's our EMF that was induced by taking just one coil and being, but we changed the area. So we had to make something change, and we just changed the area, and that's how we induce some voltage. All right, let's take a look at the second one. Number 11. A rectangular coil, 0.055 meters by 0.085 meters, is positioned so its cross-sectional area is perpendicular to the direction of the magnetic field, B. All right, so I have this time it's I'm going to give it a little handle. A coil, and it's 0.055. Let's see, that's the smaller ones. I'm right here, 0.055 meters by 0.085 meters. All right, and this is perpendicular to the direction of the magnetic field. So if I've got it flat on the paper, it must be sticking up, going up, or sticking down, going down. Okay, so that's my coil, and it says if the coil has 75 turns, okay, so there's going to be 75 of those. So N is 75, and a total resistance of 8.7 ohms, and the field decreases at a rate of 3.0 Tesla per second. What does that mean? All right, I know it's Tesla, so that must be B. So I've got B over time, okay? B over time, the change of B over time is 3.0 Tesla per second, okay? Tesla per second. Now, what's the magnitude of the induced current? What's the current induced? I we use for current. What's the current induced? Well, my equation is for induced voltage, and I know induced voltage is equal to induced current times resistance. So we're using EMF, fine. So for current, all I have to figure out is the EMF, the voltage induced, and divided by the resistance. So the current is going to be the EMF, which is voltage, divided by the resistance. So let's figure what the EMF voltage is, just like we did in the previous problem. All right, so what's our equation? Our equation, here you go, your volts generated or your EMF. Move this up here a little bit. Here we go. I got EMF is equal to negative the number of turns times the change of the field times the area all over the time. And notice that they gave me this part already. That's what they gave me already. So cool. So all we have to do is multiply that times the number of turns times the area. Okay, they didn't give us the area. No, but they gave us a length and the width. So area, if you remember for a rectangle, is just going to be length times width. Okay, where this side is the length and this side is the width. Hope you remember that. Okay, so let's do that. We've got 75 turns. I got negative 75, And then this guy here was 3 Tesla per second, all that per second. And then my area, I've got to multiply these two dimensions, 0.055 times 0.085. There we go. That's all we have to do. So let's plug that in. Let me clear that. I got 0.055 times 0.085. There's my area. Times, I've got 3 Teslas here, and then I got 75 turns, times 3 times 75. Okay, now that gives me my voltage, my EMF voltage, 1.05, 1875 volts. There we go. That's my EMF induced, my induced EMF. And since we know V equals IR, I is V over R, so we're going to take the EMF voltage and divide it by the resistance. Okay, so the induced, I'll put here induced current is just the EMF in volts over the resistance. So I'm going to take this number I just computed, 1.05187 divided by the resistance, which they gave us was 8.7 ohms. 8.7 ohms. Okay, and this is volts. So let's take that and say divide this by 8.7. There we get 0.12 amps. 0.121, I guess, amps. Okay. Remember that milliamps is what we really deal with in terms of safety. So this one here is like 121 milliamps. Okay, but it's fine to have it as 0.121 amps. All right, last problem. And this, for this section, is number 12. Number 12, here we go. It says a 52 turn coil. Okay, I'm going to start right away. I got N is 52 turns. Has an area of, oh, they gave us the area right away, 5.5 times 10 to the negative third. So I'm going to say the area is 0.0055. Is that right? 5.5 times 10 to the negative 3 meters squared. Is dropped from position of 0 Tesla to a new position of 0.55 Tesla. So here they tell you, here's what we changed. We changed the magnetic field strength. So my delta B is got to be the final minus the initial. So minus 0 just makes it 0.55 Tesla. If the displacement occurs in, there's our time, seconds. So delta T is equal to 0.25 seconds. And the area is perpendicular to the magnetic field line, so we know it's going to be the maximum. What is the resulting average EMF? What's the EMF again? All right, so we just go back to our original equation. Let's see if I have room right here. EMF, or the voltage induced, is equal to negative N, the number of turns, times the change in magnetic field. Magnetic field times the area all over the time. Okay, so we've got 52 and our magnetic field is 0.55 Tesla. And we're going to multiply that by the area, which is 0.0055 square meters, all divided by 0.25 seconds. All right, so let's do that. Okay, so 52 times 0.55 times 0.0055, all that divided by 0.25. And we get a negative 0.6292 volts. So looking at our, looks like you got to have two significant figures. So I've got negative 0.63 volts. So more than half a volt was induced. I'm checking here. And there you go. So hopefully you see, and I do encourage you to play with the FET so you can actually see what's going on as you're moving. Actually, it only lets you move the magnet, but still you're changing the magnetic field strength within those coils, and you're inducing a voltage, which then produces the current, which then turns on the light bulb. All right. So let me know if you have any questions or if you want to meet with me. See you next time.